So the characteristic of nonlinear SVM is this. It's the kernel. The whole choice is the kernel. If you don't choose your kernel, they're going to give you this RBF kernel. And you can choose a polynomial kernel. There's a lot of research just to change the kernel a little bit. They did a better job. You can publish paper for sure. Okay, that's one thing. You have polynomial kernel, and the book only give one type of polynomial kernel, square. You don't want to get too complicated. You know, why square is the best? Because square always have a minimum and the maximum, right? If you get to the cubic, you get a multiple value and the multiple peak. Your algorithm may not work out. It's just trapped in some local minimum instead of a global minimum. You could trap it, could not get out. That's why they choose square. The question is this. When you use the nonlinear, when you should use kernel, when you should not use kernel. When you use the linear separate, when you should not use the linear separate. How do you know which one is the best choice? Have any clue? How do you know in the first place? Visualization. There's nothing better than you visualize it. The visualization is even better than statistics. Okay? You see it. You see how it can be separated the best. You know what those functions will do, and then you know what to choose, right? If you look at those spread it like into hyperbolic way, you know, spread the distance away, and then you probably use a hyperbolic one. That's the one we choose. The example I gave. If you look like more from the circle, the distance, like a normal distribution with someone around the average, someone far away from the average, you're going to use this RBF, right? The Gauss distribution. Those things all come from the visualization of the data. Then you make your first shot of choice. You don't want to always try and waste your time. But visualization is your start point. That's why we want to introduce that, especially for low-dimensional data. But high-dimensional data, what you do the primary component analysis first to see which one is the real telling, the instructive or informative set of attributes. But each time you do 3D, how about that? And then you change to another 3D from the primitive component to the next one, and then you're going to get an idea. First, should it be linear or nonlinear? Most likely, but the default is nonlinear. Because nonlinear could always include the linear if it come back into a plane, right? And then which type? There's not many types. Either circular, like elliptic, or hyperbolic, pretty much like this, right? Could be parabolic, because we don't want the curve too complicated. You don't have to. I would think a quadratic is good enough. Make sense? Yeah, it just depends. It's elliptic, then it's like a circle. Or hyperbolic is going to two directions. Parabolic is set up by two-way. Let me be more specific. What's the advantage of use kernel method and not kernel method? There's only two branches in the algorithm level. One level, you have to walk through all the instances. In that way, they did not really get the so-called the support vector machine, the SVM. If we understand the support, it means you are using the Lagrange's multiply method. You only pick those really touch those marginal lines, right? Those points are few, not all the set. In each time, it might be 2, 3 points, 4 points. It really matters. The rest doesn't matter. It's just which side you belong to, right? In that way, Lagrange's method, it's good when you have a lot of instances, like thousands of instances. You do not want to walk through all the instances. You do the cubic, because each time an algorithm will be, let's say you have 1,000 instance training. And the thousands, the cubic is 1,000 times 1,000 times 1,000. That's a billion times of operation by one line. That's very expensive, right? Then if we use the support vector machine, among these thousands of instances, might only have 3, 4. That matters to set the boundary, right? Right? That method will be very efficient. That's why Lagrange is smart to let you know each time you must have the equality. Only a few will matter. The most are 0. Those are numbers 0. Another way, of course, is going to be how to use all the instance. Not basically it's shoot at every choice of your instance to see what's the best. But that is also good in some way if you have a lot of attributes. The column is not, but a few rows. You don't have many instances. For example, like medical data, you got a lot of attributes, but however, you don't have a lot of instances because the data are too expensive. And in that case, the other method is better, called the regression method. And that regression method, they will just walk through all the instances. And then you're going to find the answer from all the instances. This sometimes is powerful. For example, if you have 5 different classifiers, each classifier, remember that, use an independent data set. And each of them have 70% of accuracy. If you joined this, then you vote. The 5, the majority vote. If there's no conflict, that's fine, you don't vote. But if there's a conflict, somebody says A class, someone says B class, now let's the 5 vote. The majority win. So how much you can improve the accuracy? In theory, when these are all independent. That's easy statistics, right? Easy statistics. The point is completely independent. That's not possible because they are, put it that way, if the data set is best, you can only 70%. Doesn't matter how do you going to back it up, it's still 70%. If the data itself has 30% of training example are wrong, doesn't matter how good you are, you're still 70%. Doesn't matter how you're going to do it, right? In other words, if you all follow me, if I told you the knowledge is 30% wrong, doesn't matter how good you are a student, you got 70% wrong. Are you with me? So that is a big theoretical hypothesis, but still help. If it's the error comes from your computation, that really help. You use 5 classify, use different data set, use different algorithm, that will be compensate each other, reduce your error significantly. That's one of the best we're going to talk next week is the ADA boost. ADA boost probably is the best so far. In the wake at least. And the boost game is best off-the-shelf classified in the world so far, and it's probably ADA boost. That's what I'm talking about. A lot of research and also commercial people like IBM, Microsoft, Google, Yahoo, no doubt, IBM. They're all competing in this field to see who they win the game. So they all have their own tool. Boosting user class work as a weak learner, but what they have all different. What is weak learner? What's a strong learner? It's just basically sometimes a lazy learner. Sometimes they call it aggressive learner. That means like the nearest neighborhood, they're the lazy learner. They don't learn until you need to use it, until the test comes in. Then that's the difference. And the other model-based is called the ego learner. You build the model first. Then when it comes, you just fit it into the model.